Hello everyone, I'm Umberto Michieli from the University of Padua in Italy, and today I'm presenting our last paper entitled Continual Semantic Segmentation by a Repulsion Abstraction of Sparse and Disentangled Latent Representations. First of all, I'm going to briefly introduce the class incremental continual learning task, which we will focus on. In continual learning, a model is updated to learn new classes added progressively over time. Here, we need to carefully balance between forgetting of previous classes and learning of the new ones. Continual learning has been widely studied in classification tasks. Instead, our focus is on semantic segmentation, which is a dense prediction task where a label is assigned to each pixel of an image. In this case, many different scenarios arise, namely sequential, disjoint, and overlapped. To have an idea of the different setups, we assume to have learned car and bike classes, that we are currently learning the person class, and we assume that in the future we will learn the dog class, for instance. First of all, labels associated to the images containing only the classes being learned are identical for all the approaches. Labels for images containing old and currently learned classes are identical to the complete ground truth for the sequential case, while only the new classes are present for the disjoint and the overlap scenarios. Finally, images containing a combination of old, current, and future classes are used only for the overlap scenario, with only the currently learned classes labeled. Now we go through our complete architecture. Our approach is called SDR, from Sparse and Disentangled Representations. What we propose is to combine the standard task-related cross-entropy loss with other constraints to improve representations learning. The network of the previous step is used for output-level knowledge distillation, as most of the recent approaches does. Then, we design three novel constraints at the related level to promote feature discrimination across different tasks. Our main intuition is that if features are representative of their class and they are well separated, then it's easier to preserve high accuracy on them whilst accommodating future classes. First, we propose a prototype matching module to match on-batch prototypes with prototypes computed from the previous steps. Here, with prototype, I refer to the average of the class-wise feature distribution. So, in the end, we want the prototypical representations for each class to be consistent across the incremental steps. Second, we design a new way of disentangling feature, which is inspired from conjunctive learning and clustering techniques. This constraint is formed by a combination of an attractive force, which clusters features of the same class tightly around the prototype, and a repulsive force, which separates features of different classes. Third, we promote feature sparsity by applying a stretch over linear function of the normalized features to ultimately reduce crosstalk between features of different classes. Overall, we constrain features of the same classes to be tightly clustered, to be spaced apart from features of other classes, and to be sparse. In this way, we preserve geometrical space, since few channels are active, and expressiveness, since features are divided into well-separated clusters. Then, it will be easier to accommodate the latent representations of future classes. In the experiments, we extensively analyzed our approach on Pascal VOC 2012 in three task incremental scenarios, where 1 or 5 incremental steps are performed. Here, we can observe that our approach outperforms the competitors almost everywhere in the sequential case, while it always wins in the disjoint and in the overlap scenarios. We can confirm this also by the qualitative results reported below, where SDR can recognize the buses in the first two figures and the car in the last one, differently from the competitors. Similar considerations also hold for the experiment on ADE20K, where our approach can outperform competitors, especially when multiple steps are involved. In conclusion, we analyzed the challenging task of continual semantic segmentation, and we tackled it with three main contributions. First, we proposed to match prototypes to preserve geometrical spacing. Then, we proposed a constructive learning module for accurate clustering and separation of feature representations. Finally, we introduced a sparsity constraint to reduce interference across the channels. In this work, we jointly tackled sequential, disjoint, and overlap scenarios, achieving state-of-the-art results on a variety of tasks and datasets. That's all. I leave here some further references to the paper webpage and to the code. We look forward to meeting you in the live session. Thank you.